All right, strap in everyone, because today's deep dive takes us right into the heart of quantum networking. We're looking at a paper that's all about boosting the efficiency of these systems, and the researchers are using some seriously powerful math to do it.
Yeah, it never ceases to amaze me how we can take these really abstract mathematical models and use them to tackle the nitty-gritty engineering challenges of actually building these networks.
It's like building a bridge between the theoretical and the practical.
Yeah.
And in this case, that bridge is made of queuing theory.
Exactly. And this paper digs into a really clever system, uses entanglement to speed up communication. But here's the cool part. It can also switch back to classical methods if it needs to. So it's way more robust and adaptable for, real-world situations.
So it's like having the best of both worlds. But I'm guessing managing a hybrid system like that throws up some pretty interesting mathematical puzzles.
Oh, absolutely. Think about it. You've got two queues. One, let's call it QA, and that holds your regular messages just waiting to be sent. Then you've got the other one, QB, and that's where you're storing these entangled qubit pairs, the bell pairs. They're like the nitrous boost for your data transfer, ready to kick in when you've got them.
Okay, so I'm picturing these two queues, like working side by side. But I'm sensing a but coming. Those bell pairs, they're not exactly known for their stability, are they?
You're right on the money there. They're super fragile, decay really quickly, which means QB is constantly changing, way faster than QA, which is relatively stable. And that difference in timescales, well, that's one of the really big challenges the researchers are tackling in this paper.
Yeah, I can see how that would make for a pretty complex system to try and model. It's like you're trying to analyze a system where some parts are moving at the speed of light and others are practically standing still.
That's a great way to put it. And to get a handle on it, the researchers used a technique called stochastic averaging. It's a really neat tool for understanding how the super fast dynamics of one part of a system end up impacting the slower parts.
So they're basically saying, let's zoom out a bit and look at the average behavior of that crazy fast QB and see how that affects the more laid-back QA.
Exactly. By focusing on the average, you kind of smooth out all those rapid-fire changes, and that gives you a much clearer picture of how the two queues are actually interacting with each other.
Like, when you take a long exposure photo of a busy street at night, you get all the streaks of light from the cars, but you don't see the individual cars themselves, but you can see the overall flow of the traffic.
That's a perfect analogy. So now, the first big result they get in the paper is proving a functional law of large numbers, or FLLN, for this two-queue system. It's a pretty fundamental theorem in probability theory. It describes the long-term average behavior of a random process.
So if I'm getting this right, the FLLN gives us a way to predict, on average, how QA is going to behave, even as the system gets bigger and bigger, with more and more messages.
Precisely. And the theorem says that as the system scales up the scaled length of QA, it can be approximated by a deterministic function. And this function, well, it's defined by a specific kind of equation called an ordinary differential equation, or ODE.
Okay, wait, let's unpack that for a second. So you're saying it's a really complex random system with these two queues going at totally different speeds. It can be captured by a simple ODE.
That's the beauty of it. And this ODE does a fantastic job of capturing how all these different factors play together. You've got the rate at which messages are coming in, the rate they're processed classically, the rate they're processed using entanglement, and even the rate at which those bill pairs are decaying.
So it's like we've taken this whole messy system and boiled it down into a single mathematical formula.
Right. And the way they prove this FLLN, well, it involves a really neat analysis of the occupation measure of QB. This measure tells us how much time the fast process spends in each of its possible states.
So it's a way of characterizing the distribution of all those rapidly fluctuating bell pairs.
Exactly. What they were able to show is that as you scale the system up, that occupation measure, it converges to a predictable distribution. And that convergence, that's crucial because it lets us link the average behavior of QB to what's going on with QA in the long run.
It's like saying, even though QB is going haywire on a microscopic level, on a bigger scale, its behavior is actually pretty predictable.
And that predictability is what allows us to get that nice simple ODE that describes the average behavior of QA.
I can see where this is going. The practical implications are huge. If you're designing a quantum communication network, you've got to know how the message queue is going to handle different loads, right? And this theorem gives you a really powerful tool to predict that and optimize it.
Exactly. It's a fundamental building block for understanding how well these networks perform.
But they didn't stop at the FLLN, did they? They went a step further and proved a functional central limit theorem, or FCLT, for this system.
And that's where things get even more interesting. While the FLLN tells us about the average behavior, the FCLT zooms in on the fluctuations around that average. It's like looking at the ripples on a pond after you throw a stone in.
So it's not just about knowing the average water level. It's about understanding how much the water is sloshing around.
You got it. And the FCLT says these fluctuations, after you scale them appropriately, can be approximated by a Gaussian process.
Now, we've talked about Gaussian processes before on the show, right? They're those super useful mathematical objects that pop up all over statistics and probability theory.
And them showing up here really speaks to how powerful and versatile they are. What the FCLT is saying is that even though the system is complex and random, the fluctuations around that average behavior, well, they actually follow a very beautiful and predictable structure.
And to get specific, that structure, it's governed by a stochastic differential equation, an SDE. That's an equation that describes how random events influence the way a system changes over time.
And this particular SDE, it captures how variations in message arrivals, service times, and even those pesky bell pair decays all contribute to the fluctuations we see in QA.
So we're not just saying, oh, there are random fluctuations. We're saying those fluctuations are random in a very specific, mathematically describable way.
Exactly. And this mathematical description, it gives us a powerful tool for figuring out how robust the system is. We can use it to work out how likely an extreme event is, like QA overflowing, which is super important if you're designing a network that needs to be reliable.
Yeah, it's like knowing the odds of your internet connection dying right in the middle of an important video call. You want to make those odds as small as possible, and the SLT gives you the tools to do that.
Absolutely. Now, proving this FCLT, it wasn't exactly a cakewalk. It involved solving a Poisson equation. That's a special kind of differential equation you find all over physics and engineering. And they also used a pretty heavy-duty math tool called the Martingale Central Limit Theorem.
I'm sensing a theme here. Martingales seem to be like the unsung heroes of probability theory, popping up everywhere.
They really are. They represent this idea of a fair game where your expected winnings at any point are equal to what you've already won. And they have this amazing property of being memoryless, which makes them ideal for modeling random processes.
So in this case, the Martingale Central Limit Theorem is what lets us connect the microscopic details of the system, all those random arrivals and departures, to the macroscopic behavior of the fluctuations, that Gaussian process we were talking about.
It's a perfect example of how abstract math can be used to understand and predict what's happening in real systems.
Okay, so we've got this 2Q system with entanglement giving things a speed boost when it can. We've got the FLLN telling us about the average behavior, and the FCLT giving us the lowdown on the fluctuations. Sounds like we're building a pretty complete picture of how these networks tick.
We are, but don't forget, these theorems are really just the beginning. There's a whole world of mathematical detail underneath the surface, waiting to be explored.
Which is exactly what we're going to do next. Let's roll up our sleeves and get into the nitty-gritty of these proofs, see how all the gears turn in these mathematical machines.
Sounds good to me. Let's dive into the fascinating world of stochastic analysis and see how it sheds light on these quantum communication networks.
Okay, so let's dig into this functional law of large numbers proof. Where do we even start with something like this?
Well, a good place to begin is with the stochastic differential equation, or SDE, for the scaled Q length at QA.
Right, because that SDE, it captures the core dynamics of the whole system.
Exactly. Remember, we scaled the system using a parameter n, which is essentially a measure of the system's size. The bigger n gets, the closer we get to that deterministic behavior described by the FLLN.
So it's like n is a magnifying glass, right? Let's just zoom in and out to see how the system behaves at different scales.
Perfect analogy. And we define this scaled process, we denote it by yn, and it includes both the scaled Q length of QA, that's YNA, and the Q length of QB, YNB.
Okay, so yn is like a vector then, keeping track of the state of both Qs.
Right. And with stochastic averaging, we're really focusing on this yn process. We want to see what happens to it as our scaling parameter n gets really big.
So basically, we're letting the system grow and watching how its behavior changes.
And the key to understanding this evolution is looking at the generator of the yn process, which is denoted by ln. The generator, it describes those tiny changes in the system's probabilities over time. It tells us how likely the system is to jump from one state to another.
It's like a map of all the possible routes the system could take.
Now, the form of this generator, Ln, It shows us that the Q length of QB, that's YNB, it changes super fast at a rate proportional to n.
Which makes sense because QB is dealing with those rapidly decaying bell pairs.
But here's the interesting part. The Q length of QA, that's YNNA, it changes much more slowly. Its behavior is actually tied to the average behavior of QB of YNB.
Right, because QA can only use those entangled pairs when they're actually there. The rest of the time, it has to rely on those slower classical methods.
Exactly. And that's where this idea of averaging the dynamics of that fast Q comes in.
So we're smoothing out all the crazy fluctuations in QB to see how they affect the more relaxed dynamics of QA.
Now, to make this averaging more formal, we introduce a linear operator, BY1. This operator, it represents the generator of a birth-death process, which basically describes how that fast Q, YNB, behaves when the Q length of QA is fixed at a certain value, which we call Y1.
Hold on, let me make sure I'm following. So we're essentially isolating QB, pretending QA is staying still, right?
Yeah, you got it. It's like saying, let's freeze QA for a moment and just watch what QB does on its own under those fixed conditions.
And by doing that, we can figure out the stationary distribution of QB, which tells us the long-term probabilities of finding it in each of its possible states.
And that stationary distribution, we denote it by, it's a key piece for describing the deterministic limit of that slow Q, YNA.
So by figuring out how QB behaves in isolation, we actually gain insights into the long-term behavior of QA. It's like understanding the parts to understand the whole.
Now, the intuition behind stochastic averaging, that's pretty straightforward. But to actually prove the FLLN rigorously, you need some pretty careful math arguments.
Of course, we can't just hand wave and say, oh, it works because we averaged something.
Yeah.
We need to show the math actually checks out.
Right. And a big part of that proof involves showing that the sequence, YNIN, that it's relatively compact. That's the occupation measure of the fast variable, YNB.
Okay, hold up. What exactly does it mean for a sequence to be relatively compact?
So relative compactness, it's a property that guarantees we can find a convergent subsequence within our original sequence. Basically, it means that the sequence isn't running off to infinity and that there are limit points we can actually study.
So it's like making sure our mathematical objects are well behaved so we can actually analyze them as the system grows.
Precisely. And we show this relative compactness by first checking something called the compact containment condition for YNA. This condition makes sure that for any tiny probability, like super small, let's call it A, we can find a big enough bound such that the probability of YNA going beyond that bound within a finite time, it's less than that tiny A.
So it's like saying, no matter how small a probability you choose, we can always find a fence to keep the process contained with a probability greater than 1A.
Exactly. It's how we tame the process, make sure it doesn't go wild.
Okay, so once we've got that compact containment for Y and A, then we look at the relative compactness of those random measures.
Right. And we do that by checking the relative compactness of what are called their mean measures. These mean measures, they tell us about the average behavior of those occupation measures.
So it's all about understanding how these measures change as the system gets bigger and bigger.
Exactly. And once we've got relative compactness for both YNA and WIN, then we know that the pair, YNAN, is jointly relatively compact.
So we've shown our sequence is well behaved. It's got those limit points we can study.
Right. And figuring out what those limit points actually are, well, that's the next step. And for that, we need some heavy-duty tools from stochastic analysis.
Sounds exciting. Bring on the big guns.
One of the most powerful tools we have is Theorem 2.1 from a paper by Kurtz back in 1992. It's all about averaging for martingale problems.
Martingales again. They seem to be the key to unlocking all these mysteries in probability theory.
I know, right? And in stochastic analysis, they're essential for connecting how a stochastic process changes to its long-term behavior.
So how does this Kurtz theorem help us here?
Well, this theorem lays out conditions that allow us to describe the limit points of a sequence of stochastic processes using martingales.
It's like a translator, helping us understand the language of stochastic processes by converting it into the language of martingales.
Exactly. So if we apply Kurtz's theorem to our problem, we can show that any limit point, YA, of our sequence, YNAA, it's got an associated martingale. Specifically, for any suitable function f, this expression, FYAAC, it's a martingale with respect to a specific filtration.
Wait, hold on. Let me make sure I'm following. So you're saying this expression, which involves the limit point YA and that limiting occupation measure, it has this special property of being a martingale.
Precisely. Here, a of y a of z is an operator that describes the deterministic dynamics of ya, and a d a x dz represents the limiting behavior of the occupation measure.
So it's like we've taken this really complex stochastic process and distilled it down into something simpler, something that has this nice martingale property.
And the key point is that this martingale property, it lets us figure out the relationship between y and o. And that's what leads us to the way we characterize that deterministic limit in the FLLN.
So the martingale is the link between all those tiny details of the stochastic process and the overall behavior described by the FLLN.
Beautifully put. To get the full picture of that limit, we need to bring in another operator, b. This one captures the average dynamics of the fast variable, y and b.
So we're back to averaging again, this time focusing on that fast variable.
Right, and this b operator, along with that stationary distribution we figured out earlier, it helps us represent the limiting measure in a concrete way.
We're taking all the pieces, the stationary distribution, the averaging operator,
Right.
and putting them together to describe that limiting behavior.
Exactly, and this concrete representation of O, it lets us write that martingale associated with y, purely in terms of ya.
So we've gotten rid of that fast variable and expressed the martingale just in terms of the slow variable.
And from there, we use the properties of martingales to finally get that ODE that governs the deterministic limit of the slow q, YNA.
Which is the exact equation we had in the FLLN, the one that tells us how the average length of QA changes over time as the system gets bigger.
Exactly. It's a pretty amazing result when you think about it. We started with this crazy complex stochastic system, two Qs running at different speeds. And through some careful analysis, we end up with this simple deterministic equation that captures how it behaves on average.
It's like we tamed all that randomness and found the underlying order.
And that order lets us predict and optimize how these networks perform, which is crucial for building faster, more efficient, more reliable quantum communication technologies.
I know we've only just scratched the surface of this FLLM proofs, but it's already clear how powerful these math tools are.
Absolutely. And we've only just begun. Next, we're diving into the equally fascinating world of the Functional Central Limit Theorem, which will give us even more insights into how these networks operate.
I can't wait. Okay, so we've covered a lot of ground with that functional law of large numbers, but now it's time to tackle the Functional Central Limit Theorem, the FCLT.
Right. The FCLT, it's what lets us zoom in on those fluctuations around the average behavior that we were describing with the FLLN.
It's like we've got this map of the terrain from the FLLN.
Yeah.
Now we're using the FCLT to get a closer look at all those little hills and valleys.
A perfect analogy. And what the FCLT tells us is that these fluctuations, if we scale them the right way, well, they can actually be approximated by a Gaussian process. We're going to denote that by W.
So all those seemingly random changes in the Q length, we're actually showing they follow a specific pattern, a pattern we can predict.
Exactly. And that pattern, well, it's captured by a stochastic differential equation, an SDE, describes how those fluctuations change over time.
So it's like we found a mathematical formula for the noise in the system.
You could say that. So to prove the FCLT, we start by defining this centered and scaled process. We'll call it WN. It measures how much the scaled Q length, YNA, deviates from its deterministic limit, YA.
So WN, it's basically showing us how much the actual Q length is bouncing around that average behavior predicted by the FLLN.
Exactly. And the really cool result of the FCLT is that this WN process, it converges in distribution to that Gaussian process W as n gets bigger and bigger.
So as the system grows, those fluctuations, they start looking more and more Gaussian.
Precisely. Now, to prove this convergence, we have to get into the nitty-gritty of the relationship between Wn and that fast variable Ynb. Remember, that's the one responsible for all those really rapid, almost chaotic fluctuations.
Right, because those fast changes in QB are ultimately what's driving the fluctuations in QA.
Exactly. And to uncover this relationship, well, we use a pretty clever technique that involves solving a Poisson equation.
Poisson equations seem to be popping up everywhere in this paper.
Yeah.
They're like the Swiss Army knives of mathematical physics, I swear.
They really are. You find them in so many different areas. Usually when you need to find a function that satisfies a specific differential equation with some boundary conditions.
So what's the Poisson equation we need to solve in this case?
It's the one associated with the generator of that fast process, YNB, where we treat the slow variable YNA like a fixed parameter.
So again, we're freezing QA in time, just looking at how QB behaves under those conditions.
Right. And the solution to this Poisson equation, we denote it by FY1, It lets us rewrite the expression for Wn in a way that separates out the deterministic part, the part governed by the FLLN, from the random fluctuations.
So this Poisson equation solution is like a filter, separating the signal from the noise.
Perfect way to put it. And this separation allows us to look at the convergence of Wn by breaking it down into these smaller, easier to manage pieces.
Divide and conquer, a classic math strategy.
Absolutely. So we look at the convergence of three terms: the martingale term, then a term related to that Poisson equation solution, and lastly, a term that comes from the generator of Yn.
All right, let's tackle them one by one. Starting with the martingale term. How do we show that it converges to the right Gaussian process?
For that, we use another powerful tool from probability theory, the Martingale Central Limit Theorem, or MCLT.
Martingales strike again. They really are the workhorses of this whole analysis.
They really are. The MCLT gives us conditions under which a sequence of martingales converges in distribution to a Gaussian process. And in our case, we carefully check that the martingale term, we'll call it a manton, that it meets those conditions.
So we're basically showing that the random fluctuations captured by this martingale, they start behaving more and more like a Gaussian process as Poisson grows larger.
Exactly. And to use the MCLT, we need to analyze something called the quadratic variation of man, which measures the total fluctuations of the process over time.
It's like keeping track of how much the process is jiggling around.
Right. And what we find is that the quadratic variation of Mn, it converges in probability to a deterministic function, which is defined in terms of the system parameters and that solution to the Poisson equation we talked about earlier. We'll call this function f of t.
So as it increases, the total fluctuations of this martingale, they become more and more predictable.
And that convergence is essential for using the MCLT to prove that Mn converges to that Gaussian process we're after.
Okay, so we've handled the martingale term. What about the next one, the one with the Poisson equation solution?
Ah, yes. That term, Fyn too, it captures how much the fast variable, Ynb, contributes to the fluctuations of Wn.
And intuitively, this term should just disappear as n grows large, right? Because we're trying to show those fluctuations converge to a Gaussian process that doesn't depend on that fast variable.
Exactly. And to prove that it does converge to zero, we use the fact that f is the solution to that Poisson equation connected to the generator of Ynb.
So we're using that link to the Poisson equation to show this term becomes insignificant as the system scales up.
Precisely. We rewrite it in a way that highlights its dependence on Ynb, and then we use the properties of Ynb, along with some careful probability arguments, to show that it converges to zero in probability as n increases.
Another piece of the puzzle falls into place.
Now, the last term in our rewritten expression for W on, that's 1 earn ein a fyns ds.
And that one comes from the generator of Yn, right? Captures how the slow and fast variables interact.
Exactly. To show this term goes to zero as well, we use a combination of things: Taylor's theorem, properties of the derivatives of f, and the fact that both Yna and Ynb converge to their respective limits as n increases.
It's impressive how the researchers managed to wrangle all these different mathematical tools to prove the convergence of each term.
It really speaks to the power of calculus and the careful design of the proof.
So we've shown that all three terms in our rewritten expression for Wn, they converge to their correct limits. So does that mean we've proven the FCLT?
We're almost there. We've shown those fluctuations of Wn become more and more Gaussian as n gets larger. But to really nail down the convergence of Wn to that Gaussian process, W, we need one more ingredient, and that's tightness.
Tightness. It seems like that concept pops up a lot when we're dealing with convergence of stochastic processes.
It does. Tightness basically guarantees that our sequence of processes, those Wn, they don't escape to infinity. It ensures that any limit point we end up with is well behaved.
So it's like making sure our mathematical objects stay within the boundaries of a well-defined mathematical space.
Great analogy. And to check for tightness, we use a bunch of tools like the Grunwald-Bellman inequality, the modulus of continuity, and that compact containment condition we established earlier for Wn.
So we're making sure Wn doesn't do anything crazy, like sudden jumps or oscillations that would prevent convergence?
Precisely. And once we've got tightness, we combine that with the convergence of each term in our rewritten expression for Wn, and then we can finally say, yes, Wn converges in distribution to the unique solution of that SDE that characterizes the Gaussian process W.
It's amazing how all the pieces fit together so perfectly.
You know, this Gaussian process limit, it's not just some mathematical curiosity. It's really important for understanding and designing real quantum communication networks.
Because it gives us a way to measure the uncertainty and variability in the system, which is critical for building networks that are robust and reliable.
Exactly. We can use this Gaussian process to analyze things like the likelihood of queue overflow, estimate waiting times, and even tweak the system parameters to hit specific performance targets.
It's a really powerful tool for connecting the theoretical with the practical.
It really is. And the authors of this paper, they even hinted that their model could be used in other quantum communication scenarios, like when you're dealing with the distribution of graph states.
So this mathematical framework, it could shed light on all sorts of quantum communication challenges.
Absolutely. A real testament to the elegance and power of math.
Well, I think we've done a pretty deep dive into this paper today. We went through the FLLN, the FCLT, and all the intricate maths behind those proofs.
Yeah, we saw how stochastic averaging, martingale theory, and even Poisson equations all come together to help us understand these complex systems.
And we talked about how those theoretical results can be applied to actually design and optimize real quantum communication networks.
It's been a fascinating journey into the world where math and quantum information science collide.
It really has. And as we keep pushing the boundaries of these fields, who knows what other mathematical gems we'll discover.
I, for one, am excited to find out.
Me too. Thanks for joining us on this deep dive, everyone. Until next time, keep those minds curious. Welcome to another deep dive. Today we're diving into the world of quantum communication networks.
Specifically, entanglement-assisted quantum communication networks.
Right.
If you can believe it.
And we'll be looking at this model for analyzing these networks from this paper called Stochastic Analysis of Entanglement-Assisted Quantum Communication Channels.
By Karim S. El-Said.
Yes.
And others.
And yeah, so for our listeners,
It's a fascinating paper. Imagine really mathematically rigorous.
a communication system that can use entanglement to speed up transmission when it's available.
Yeah, they have a really clever queuing system.
So like waiting in line for coffee.
Kind of, yeah. Instead of people, though, you have information messages waiting to be sent. And they describe this two-queue system.
Okay.
QA is the primary queue, which holds those information messages. And then QB is the service queue, which holds bell pairs.
So the bell pairs, those are the entangled qubits.
Exactly.
That help speed things up.
Yeah, think of them as like specialized resources that can dramatically accelerate the transmission of information.
Okay.
And the model considers both classical and entanglement-assisted transmission.
Doesn't entanglement decay over time?
You're absolutely right. And the model accounts for that.
Okay, good.
It incorporates the fact that entanglements have like a finite lifespan and they can decay.
That's interesting how they account for that.
Well, they do this by using something called propensity functions.
Propensity functions.
Yeah, you can find them in the paper equations 1 and 2.
Oh, we're already getting into equations.
Yeah.
I'm sure these aren't simple.
No, they're pretty dense.
Okay.
But essentially, they describe the rates at which different events occur in the system.
So like what kinds of events?
Well, for example, the arrival rate of messages,
Okay.
the rate at which messages are transmitted classically, the rate of entanglement-assisted transmission,
Okay.
and even the rate of entanglement decay.
So it's like they're trying to figure out the probability of these different events happening.
Precisely. It's a probabilistic model.
Okay.
And what's really elegant about these propensity functions is their flexibility.
In what way?
Well, the paper highlights how they can be tailored to represent various scenarios and entanglement utilization protocols.
Oh, so you can kind of adjust them to fit whatever situation you're looking at.
Exactly. They've built this general framework that can be adapted to different kinds of quantum networks.
That's smart.
Yeah, and they even give some specific examples.
Like what?
One that stood out to me is where the entanglement-assisted departure rate
Okay.
depends on both the number of messages waiting in QA and a speed-up factor denoted by M.
Speed up factor.
Yeah, it's related to a process called purification.
Purification.
So real-world entanglements aren't perfect.
Right.
they're noisy,
Uh-huh.
and purification techniques are used to like improve the quality of entanglement.
Okay, so they kind of refine it
Yeah.
to make it a more reliable connection.
Exactly, like refining it.
So M is telling us how much faster the transmission is with this purified entanglement.
Yeah, and there's a trade-off involved. Higher M means faster transmission, but it requires more resources to achieve that level of purification.
So it's a design consideration.
It is a key design consideration for these networks.
Interesting.
Yeah.
This is all really fascinating. But then they start talking about FLLN and FCLT.
Yeah.
And that's where I start to lose track a little bit.
I understand those acronyms can be a little intimidating,
Yeah.
but the concepts themselves are very intuitive once you break them down.
Okay, well, let's break them down.
Okay.
What exactly are they?
So FLLN stands for the functional law of large numbers.
Okay.
And in this context, it's used to analyze what happens to the system when the traffic load becomes very heavy.
Okay.
And to represent that heavy traffic scenario, the authors introduce a scaling parameter, n.
So as n gets larger,
Yeah.
that we're basically saying that more and more messages are being sent.
Exactly. More and more messages are being sent through the network.
Okay.
And the FLLN, as applied here, tells us that under these heavy traffic conditions, the behavior of QA,
The one holding the information messages.
yes,
Okay. Becomes more predictable.
what do you mean by predictable?
It means that the scaled queue length can be approximated by a deterministic function,
Okay.
which they denote as YA.
Okay.
It's like saying that even though individual messages arrive randomly, when you zoom out and look at the overall system with a lot of traffic, the queue length follows a predictable pattern.
So even in the quantum world with all its randomness, there's some order to it
Precisely.
when things get busy.
When things get busy, yeah.
Okay.
And this deterministic function, YA, is described by a specific ordinary differential equation, or ODE,
An OD. Okay.
which you can find as equation 11 in the paper.
Equation 11. Got it.
Yep.
But of course, the real world isn't perfectly predictable. There's
Right.
always fluctuations.
Arr.
Is that where FCLT comes in? Exactly. You're on the right track. FCLT stands for the Functional Central Limit Theorem. And it helps us understand those fluctuations around the deterministic limit described by the FLLN.
So we have this like smooth, predictable curve representing the average behavior.
Yeah.
And FCLT is telling us how much the actual queue lengths might jump around.
Yeah, precisely. It gives us a way to quantify and analyze those deviations from the average.
Interesting.
What's remarkable is that they found an explicit solution for the FCLT in this case.
Oh, wow.
They show that the fluctuations can be described by something called a Volterra-Gaussian process.
A Volterra-Gaussian process?
Yeah, it's
That sounds complicated.
it is.
Okay.
But the key takeaway is that it gives a very precise mathematical description of how the queue length fluctuates even under these heavy traffic conditions.
And why is that so important?
Well, having this detailed understanding is crucial for designing efficient and reliable quantum communication networks.
Makes sense. If you can predict those fluctuations, you can design systems that are more robust.
Exactly, less prone to errors. Right.
And this is just the beginning. The paper goes on to explore the practical implications of these findings in much more detail.
I'm ready to hear more.
All right, let's move on then
Okay.
to the next section.
Sounds good.
I think what's really impressive is how they bridge the gap between theoretical modeling and practical design considerations.
Mm-hmm.
They don't just give us these equations, they actually show how they can inform those real-world engineering decisions.
Yeah, so it's like they're providing a toolkit
Exactly.
for building these quantum networks.
A toolkit for building efficient quantum networks.
And they get into this in the discussion section, right?
Yeah, section 5 of the paper discussion, that's where this connection becomes really clear.
Okay.
They talk about the versatility of their model,
Huh?
highlighting how the propensity functions can be fine-tuned
Great.
to represent different entanglement utilization protocols.
So we're moving away from like the perfect world
Right.
of entanglement
Right.
and getting into the nitty-gritty
Precise.
of noise and imperfections.
Yeah.
Yeah, and they bring up purification again,
Oh,
emphasizing how that speed-up factor, M,
right.
reflects the trade-offs involved in choosing different purification protocols,
It's like
like optimizing a recipe.
yeah.
You can spend more time refining the ingredients to get a better outcome, but it comes at a cost.
Right,
The
exactly.
perfect analogy.
And they talk about existing models for calculating fidelity, right,
They do.
for these purification protocols.
Yeah, they underscore the importance of those models for calculating the average fidelity achieved through different purification protocols.
So we can actually figure out M
Yeah, this allows us to actually determine the value of M for different scenarios.
Okay.
And make those informed design choices.
So it's not just theoretical.
It's not just abstract theory. We have concrete tools to work with.
Exactly.
Yeah.
They also talk about how the model works with different arrival rates.
They do.
And classical service models.
Right. Yes. They discuss how the model accommodates various scenarios for message arrival rates and classical service models.
And this really captures that interplay between the two.
It does.
Classical and quantum.
It captures the interplay between classical and quantum communication in a very comprehensive way.
Then there's this section on performance-based quantum communication system design.
Yes.
And it seems like they're really talking about optimizing these networks.
That's exactly what they're talking about.
Okay.
Optimizing these networks to meet specific performance goals.
So you can basically tweak those parameters?
Yes.
To hit certain performance targets?
You can engineer the network's behavior by tweaking those parameters.
And that's where they talk about effective service rate.
Exactly.
Okay.
They introduce the concept of effective service rate.
Which I guess is like a key way to look at the performance?
It is. It represents the steady state expected service rate, considering both classical and entanglement-assisted transmission.
So it's like a combined metric. That gives you the overall picture.
It gives us a clear way to quantify the overall efficiency of the network.
There's this example where they use those specific propensity functions, and then they solve for the steady state Q size by adjusting the entanglement generation rate and the speed up factor.
It's a powerful demonstration of how their theoretical model can be translated into those actionable insights for design.
So it's like a roadmap.
It is. It's like a roadmap.
But then they take it even further.
They do. They go even further, and they discuss how the model can be adapted for other quantum communication applications beyond just entanglement-assisted communication.
See, this is what I love about deep dives. You start with one thing.
Yeah.
And you end up somewhere completely different.
Precisely. They highlight how the model can be applied to applications that utilize bipartite entanglement for tasks like teleportation switching or forming graph states.
Graph states, now those are...
Graph states are essentially multipartite entangled states, networks of entangled qubits, where the connections between them are represented by a graph.
So it's getting even more complex.
They have huge potential for quantum computing and communication.
I can only imagine.
Yeah.
And they're setting the classical service rate to 0, right?
They are in this adapted model.
Okay, why is that?
It reflects the fact that in these distributed quantum applications, processing requests often depend entirely on the availability of those entangled pairs.
Okay.
So setting the classical service rate to 0 ensures that requests are only served when entanglement resources are available.
So it's really all about the entanglement.
It is entanglement becomes the key that unlocks the processing power in these applications.
I like that.
Yeah.
The key.
And by maintaining that core structure of the original model, they allow us to leverage the mathematical insights gained earlier and apply them to this new domain of quantum communication.
Yeah, and this whole discussion section is really broadening our understanding of how this model can be applied.
It really broadens our understanding of the potential applications of this model.
Yeah, it's not just about speeding up communication.
No, it's not.
It's about understanding all these different quantum processes.
You've hit the nail on the head. The authors have given us a versatile tool for tackling the challenges of designing efficient, reliable, and scalable quantum networks.
And that's really what it's all about.
It is.
Designing these networks.
It's a testament to the power of mathematical modeling in paving the way towards a quantum future.
Okay, well, I think it's time to get into the math.
Okay.
A little. We've talked about the concepts.
Yeah.
But I know our listeners are really interested in the proofs.
I agree. We can't leave our mathematically inclined audience hanging.
Exactly.
The proofs in this paper are really quite a tour de force.
Yeah.
Drawing on these advanced techniques like the stochastic averaging principle and the martingale central limit theorem.
So let's dive into the details.
Right.
I'm really interested in how they actually prove the FLLN and FCLT.
Excellent point. Let's start with the FLLN, which focuses on proving that as the scaling parameter n grows large, remember that represents heavy traffic conditions.
Right.
The scaled Q length of QA, denoted as YNA, converges to that deterministic function YA.
That smooth curve.
That smooth curve, exactly.
Okay.
The proof cleverly utilizes the concept of occupation measure.
Occupation measure.
Yeah, it's essentially a way to track how much time the fast process,
which is,
in this case, the entanglement queue denoted as YNB,
okay,
spends in different states.
So it's not just where it is,
It's how it behaves over time.
how it behaves. Okay.
Precisely.
Got it.
And the authors demonstrate that this occultation measure converges to a product measure.
Okay.
What that means is that the long-term behavior of the fast process can be described by its ergodic moments, its average behavior over time.
Okay, but how does that connect to the slow process?
That's where the ingenuity comes in. By carefully analyzing the limiting behavior of this occupation measure, they show that the dynamics of y and a can be effectively averaged over the rapid fluctuations of y and b.
So they're smoothing it out.
They're smoothing out the noise introduced by that fast-changing entanglement queue
Okay.
to reveal the underlying predictable behavior of the message queue.
Got it.
Exactly.
That makes sense.
And this averaging leads to the conclusion that y(a) converges to that deterministic function ya, which is governed by a specific ODE as nm approaches infinity.
Okay, and that's the FLLN.
That is the FLN.
And then the FCLT builds on that.
It builds upon that foundation. It aims to characterize the fluctuations of y and a around that deterministic limit y and a.
Like those wiggles.
Those wiggles,
So
exactly.
how do they analyze those?
The heart of the FCLT proof lies in solving something called the Poisson equation.
The Poisson equation.
This equation connects the generator of the fast process with the slow variable frozen to a specific function that captures the fluctuations we're interested in. It's a complex equation, but the authors masterfully solve it, providing an explicit solution in Lemma 2.
Lemma 2.
This solution is key to their subsequent analysis.
Okay.
So they found a mathematical formula for those wiggles.
They are.
And armed with this solution, they employ the Martingale Central Limit Theorem, or MCLT, to establish that the centered and scaled process, which represents the deviation of y and a from ya, converges to a Gaussian process.
Gaussian. So we're talking Bell curves.
Exactly. They're saying the fluctuations have a specific statistical structure,
Okay.
and they go even further, showing that this limiting Gaussian process can be represented as a Volterra Gaussian process.
A Volterra Gaussian process.
A specific type of stochastic process with some interesting properties.
And I see Remark 3 mentions Brownian motion.
Yes. Remark 3 mentions that this Volterra Gaussian process can be expressed in terms of a kernel and a standard Brownian motion.
Okay, so some serious math is happening here.
The kernel essentially captures the memory of the process,
The memory.
reflecting how past fluctuations influence the present.
So it remembers.
It's a reminder that even these random wiggles have a structure and a history.
Wow.
Why is it important to understand the specific structure of these fluctuations?
Yeah, why?
Well, because it allows us to answer practical questions about the behavior of the queue.
Such as?
For instance, the authors point out that the FCLT results can be used to analyze the local times of the limiting process, which tells us how much time the process spends near certain values.
So like the likelihood of it reaching a certain point?
Exactly.
Okay.
It showcases the power of stochastic analysis to provide deep insights into the complex dynamics of quantum communication networks.
This has been really helpful,
It has.
breaking down the math.
It has been illuminated.
But I want to talk about those adaptations
Okay.
for things like teleportation
Yes.
and graph states.
I'm glad you brought that up. It's a testament to the model's versatility
Mhm.
and its potential to impact a wide range of quantum technologies.
Okay, so let's explore those a little bit more. I'm particularly curious about how they handle teleportation
Okay.
in these graph states.
So these applications leverage the unique properties of entanglement
Okay.
to achieve tasks that are simply impossible with classical communication methods.
Right, and we talked about how the key to that is the entangled pairs.
Exactly. Remember how they set the classical service rate R3 to 0 in the adapted model?
Yes.
That highlights the crucial role of entanglement as a resource.
Okay.
In these applications, processing requests or performing specific quantum operations often can only occur when entangled pairs are available.
So they're essential.
They're
Yeah.
essential. It's like having a special key that unlocks the quantum processing power.
I like that analogy.
And while the specific details of how the model is adapted might vary depending on the application, the underlying principles remain the same.
Right.
They're still using this powerful framework of propensity functions and queuing theory
To analyze the system.
to analyze the dynamics of these quantum systems.
Exactly, and the graph states are really interesting.
They're fascinating structures. Imagine a network where each node represents a qubit,
Okay.
and the links between those nodes represent entanglement.
I see.
These graph states have remarkable potential for quantum computing and communication.
And understanding how they behave is essential.
It is crucial for harnessing their power.
Right.
And it seems like this adapted model provides a way to do just that.
It does.
By modeling the creation, distribution, and utilization of entanglement within these graph state networks, researchers can gain valuable insights into their behavior and optimize their performance for specific tasks.
This is all so interesting.
It is.
But I think my brain needs a little break.
A break is a great idea. It's easy to get lost in the intricacies of these quantum systems. A break is a good idea. It's easy to get lost in all these details.
Well, it feels like we've been on quite a journey today.
It has been a journey.
Exploring these entanglement-assisted quantum communication networks.
We have.
And this paper that lays out this mathematical model.
Fascinating paper.
To analyze and optimize these networks.
Yeah, and even going beyond that, talking about how we can adapt the model for other applications.
Exactly, like teleportation.
Like teleportation.
And graph states.
Graph states.
But I want to circle back to the math for a minute.
All right.
To the proofs.
The proofs, yeah.
We talked about FLLN and FCLT.
Oh, we did.
But I think we need to unpack those a little bit more.
Okay, yeah. Let's spend a little more time on the specific techniques they use.
Yeah, like how they got those results.
Exactly.
So let's start with FLLN again.
Okay.
Which shows that under heavy traffic, the scaled Q length of QA converges to that deterministic function YA.
YA, yep.
And the key to this proof, if I remember correctly, is the occupation measure.
It is. The occupation measure is really key here.
So just remind us what that is again.
Yeah. So the occupation measure, in this context, it gives us a way to track how much time the fast process spends in different states.
Which is the entanglement queue.
Exactly, the entanglement queue, YNB. So it's really a way to characterize the long-term behavior of that queue.
Okay. And they show that this occupation measure converges to a product measure.
They do. They demonstrate that it converges to a product measure.
So what does that mean exactly?
Well, it means that the long-term behavior of that fast process can be described by its ergodic moments, its average behavior over time.
Okay.
And that's crucial for the proof.
Yeah, why is that?
Well, because it allows them to effectively average the dynamics of the slow process, YNA, over those rapid fluctuations of the fast process.
So they're basically smoothing things out.
Exactly. They're smoothing out all that noise.
From the entanglement queue.
Introduced by that rapidly changing entanglement queue.
To see how the message queue behaves.
To reveal that underlying predictable behavior of the message queue.
Yeah, okay.
So it's like zooming out to see the bigger picture where the individual fluctuations become less important, that overall trend emerges.
Right. And that leads to the conclusion that the scaled queue length of the message queue converges to that deterministic function.
Exactly. YNA converges to YA.
Governed by that ODE.
Which is governed by a specific ODE.
As n approaches infinity.
As n approaches infinity.
Which is the FLLN.
Precisely. That's the essence of the FLLN.
Okay, now what about the FCLT?
All right, so the FCLT builds on that foundation.
Okay.
It aims to characterize those fluctuations of YN around that deterministic limit.
Right.
The wiggles.
Yeah, those wiggles, exactly.
So how do they get a handle on those?
Well, the heart of the FCLT proof lies in solving what's called the Poisson equation.
The Poisson equation.
This equation connects the generator of that fast process with the slow variable frozen to a specific function that captures those fluctuations. It's a pretty complex equation, but the authors solve it masterfully, providing an explicit solution in Lemma 2. And this solution is key to their analysis.
Okay.
So essentially, they found a mathematical formula for those wiggles.
And with this formula, they can employ the Martingale Central Limit Theorem, MCLT, to establish that the centered and scaled process, which represents the deviation of YNA from YA, converges to a Gaussian process.
Okay, so the fluctuations have a Gaussian distribution.
Precisely. They have that specific statistical structure.
Like a bell curve.
Like a bell curve, exactly.
Okay.
And they go even further. They show that this limiting Gaussian process can be represented as a Volterra-Gaussian process.
Volterra-Gaussian process.
A specific type of stochastic process with some really interesting properties.
And that's where the Brownian motion comes in.
Yes. In Remark 3, they mentioned that this Volterra-Gaussian process can be expressed in terms of a kernel and a standard Brownian motion.
So there's a lot of complex math happening here.
There is a lot of sophisticated mathematical machinery at play.
But they're able to use it to describe these fluctuations really precisely.
Yeah, exactly. And the kernel in that representation is particularly insightful.
Yeah, why is that?
Because it captures the memory of the process.
The memory.
It reflects how past fluctuations actually influence the present.
So it remembers what happened before.
It remembers, in a sense, it's a reminder that even those random wiggles have a structure and a history.
That's fascinating.
And understanding the specific structure of those fluctuations is not just an academic exercise.
Right, it's important for practical reasons.
Exactly.
So why is it so important?
Well, because it allows us to answer those practical questions about the behavior of the queue.
Give me an example.
For instance, the authors point out that the FCLT results can be used to analyze the local times of that limiting process,
Okay.
which tells us how much time the process spends near certain values.
So like the likelihood of it hitting certain threshold.
Precisely, and that's crucial for designing those robust systems.
Makes sense.
It really showcases the power of stochastic analysis to provide these deep insights into the complex dynamics of quantum communication networks.
Well, I think our listeners now have a much better understanding of the math behind this model.
I hope.
From occupation measure to the MCLT to those Volterra-Gaussian processes.
It's been a great exploration of the interplay between rigorous mathematics and that cutting-edge quantum technology.
And I think it's safe to say that this is just the beginning.
Oh, absolutely.
As quantum technologies keep advancing, we're going to see even more sophisticated models.
Most sophisticated mathematical models.
To help us understand these systems.
Further deepening our understanding and expanding the possibilities in this field.
It's an exciting time to be following this.
It is a very exciting time.
So to our listeners, I encourage you to check out the paper itself.
Yes, definitely.
And all the resources that are available online.
There's a wealth of information out there.
And keep exploring.
Keep exploring, keep questioning.
And join us again next time for another deep dive.
Until then, farewell.
Farewell. Welcome back for another deep dive. You know, we're always on the lookout for the most exciting research in quantum communication. So get this. This time we're going deep on a paper that takes a look at entanglement-assisted communication, but through a completely different lens.
Oh, interesting. What's their approach?
They're using a queuing model.
A queuing model, huh?
Yeah, so it's all about understanding how to actually make these networks work efficiently. You know, how do you manage the flow of messages and these entangled qubits, those bell pairs, to optimize transmission? It's pretty cool.
Well, that's certainly a unique angle.
Right. So why should you, the listener, care about this? Because entanglement is like the secret sauce of quantum communication.
Yeah.
It has the potential to unlock faster, more secure ways to share information. But there's a catch. Those entangled states are super fragile. They're like, how do I put this, like those little soap bubbles that just, poof, disappear in a second.
I get the picture.
Yeah. And that's where this paper comes in. They're diving into the math to figure out how to manage these delicate quantum states and make entanglement-assisted communication a reality.
The math behind entanglement is, yeah, it can get pretty intense. So I imagine this paper is no walk in the park.
Oh, absolutely not. It's a real brain twister. But luckily, we have an expert with us today who can break down the complex math and extract the key takeaways.
Well, I'll certainly give it my best shot.
So let's kick things off with the basics, just to make sure everyone's on the same page. Can you give us a quick rundown on what we mean by quantum communication and entanglement?
Absolutely. So in a nutshell, quantum communication uses the principles of quantum mechanics to transmit information. And one of the most mind-boggling aspects of quantum mechanics is entanglement.
Mind-boggling is right.
It's this spooky action at a distance where two particles become linked no matter how far apart they are.
It's like they're connected by an invisible thread.
Exactly. Now, if you measure the state of one particle, you instantly know the state of the other, even if they're light years apart. And this is where things get really exciting for communication.
Yeah, it's like, whoa.
Imagine you have these two magic coins, let's call them quantum coins, that are entangled. You flip one, and instantly, no matter where the other coin is, you know whether it landed heads or tails.
Oh, that's a great analogy.
And this instantaneous correlation, that's the key to boosting channel capacity in quantum communication. We can exploit this spooky connection to send information faster and more securely than ever before.
Okay, entanglement, magic coins. I'm hooked. Now, this paper uses a queuing model to analyze these entanglement-assisted communication systems, right?
That's right.
What's the story with this queuing model? I mean, how does it actually work?
So picture this. You have two queues.
Two queues, okay.
One queue, let's call it QA, holds the messages, the information packets waiting to be sent.
Got it.
The other, QB, is where those precious entangled qubits, those bell pairs, hang out. Now here's the key. QB is what we call a fast queue.
A fast queue. That's interesting.
It's fast because those bill pairs, they have a very short lifespan. They decay quickly, so they need to be used as soon as possible. And this difference in speed between the two queues, that's a central challenge that the paper addresses.
So you have these two queues, one for messages, one for bell pairs, and they're running at different speeds. Almost like a, I don't know, like a high-speed train trying to sync up with a local bus.
Yeah, that's a good way to think about it. And to analyze this complex system with its different speeds, they use a really clever technique called stochastic averaging.
Stochastic averaging. Okay, now that sounds pretty complicated.
It is a bit technical, but essentially it allows us to smooth out the rapid fluctuations in the fast queue, the bell pair queue, and see how those fluctuations impact the slower evolving message queue.
So we're kind of zooming out and looking at the overall traffic flow rather than getting bogged down in the individual movements of the cars or the buses, so to speak.
Precisely. It's all about understanding the bigger picture, how those rapid bell pair fluctuations affect the overall efficiency of the message queue.
Makes sense. And speaking of efficiency, the paper introduces these things called propensity functions. What are those all about?
Oh, the propensity functions are crucial. They basically control the rates at which different events happen in the system.
Okay, so like events like messages arriving, bell pairs being generated, things like that.
Exactly. There are 5 main propensity functions denoted by R1 through R5. Each one represents a specific process, like the rate at which messages arrive, how quickly they're sent out, how fast bell pairs are generated, and how quickly they decay.
So it's like each of these functions governs a different aspect of the system's dynamics.
Right. And the beauty of this approach is that each function can depend on the current state of the system.
Meaning what?
Meaning, for example, the arrival rate of messages, that's R1, might depend on the size of the message queue.
Oh, so it's like a feedback mechanism.
Yeah.
Right. If the queue's getting too long, maybe the arrival rate slows down a bit to prevent congestion.
Exactly. It's like a self-regulating system, adjusting its behavior based on the current conditions.
Okay, that's pretty cool. Now, messages can be sent out in 2 ways, right? Classically, like we do now with traditional networks, and then using entanglement, which is the whole point of this paper.
Yeah.
So how do they represent those different departure rates in the model?
That's where R3 and R4 come into play. R3 represents the classical departure rate, so it's just the normal speed at which messages are sent out without any entanglement. But R4, that's the exciting one.
The entanglement express lane.
Exactly. R4 represents the entanglement-assisted departure rate, and it depends on both the size of the message queue and the number of bell pairs available.
Okay, that makes sense. So the more bell pairs you have, the faster you could potentially send those messages out using entanglement.
Right. But here's the thing, and this is where the fast queue concept really comes in. Those bell pairs are constantly decaying, so you have to use them quickly before they disappear.
It's like a race against time to harness the power of entanglement before it vanishes.
It is. And that's where those last 2 propensity functions, R2 and R5, come in. R2 controls the bell pair generation rate, how quickly we can create those entangled pairs.
Right.
And R5 represents the decay rate, how quickly they disappear. They actually model the decay process as proportional to the number of bell pairs. So the more you have, the faster they decay.
Oh, that's interesting. It's like those soap bubbles. The more you have, the faster they seem to pop.
It's a delicate balance, isn't it? You want to generate those bell pairs as fast as possible, but they're incredibly fragile.
And that fragility, that's one of the biggest challenges in building real-world quantum communication systems, right? It's not just a theoretical problem. It's a real engineering hurdle.
Absolutely. These theoretical models give us a framework for understanding these systems, but actually building them is a whole other ballgame.
Okay, so we have our 2 queues, our 5 propensity functions controlling the flow of messages and bell pairs. But the paper doesn't stop there. They dive into some pretty serious math to analyze this model. They talk about stochastic differential equations, those limit theorems. Wow. Where do we even start unpacking all of this?
Well, perhaps a good place to start is with the concept of stochastic differential equations, or SDEs for short.
All right, SDEs, hit me.
These SDEs, they're the mathematical tools that describe how the system evolves over time.
So they take all those random events, like messages arriving or bell pairs decaying, and incorporate them into the equations.
Exactly. They capture the randomness inherent in these quantum processes and allow us to study how the system behaves over time, with all its fluctuations and uncertainties.
Okay, that makes sense. But I imagine with 2 queues operating at different speeds, those equations can get pretty hairy, right?
They can, but this is where the stochastic averaging we talked about earlier comes in handy.
Right, that technique that helps us zoom out and see the big picture.
Exactly. It allows us to simplify the analysis while still capturing the essential dynamics of the system. It's like filtering out the noise to focus on the signal, so to speak.
I like that analogy. It's like listening to a symphony and focusing on the melody, even though there are all these other instruments playing in the background.
Precisely. Now, with those SDEs and the stochastic averaging in hand, the paper presents some key mathematical results that give us insights into the system's behavior. And one of the most important results is the functional law of large numbers.
The functional law of large numbers.
Yeah.
Okay, now that sounds impressive. What does that tell us about the system?
Well, it's about understanding what happens as the system gets really large.
Meaning more messages, more bell pairs, essentially scaling up the whole network.
Exactly. It tells us that as the system scales up, the behavior of the message queue, even though it's driven by all these random events, becomes more predictable. It follows a specific path described by an ordinary differential equation, or ODE.
So even with all the randomness involved, the message queue sort of settles down into a predictable pattern in the long run.
That's the idea. And this ODE, it captures the interplay between all those key parameters we discussed earlier, the message arrival rate, the classical departure rate, and that crucial entanglement-assisted departure rate.
Okay, so the functional law of large numbers gives us the average behavior of the message queue as the system gets really large. But what about the fluctuations around that average? Don't those matter too? I mean, real-world systems are never perfectly predictable, right?
You're absolutely right. And that's where the Functional Central Limit Theorem, or FCLT, comes into play.
FCLT, another impressive-sounding theorem.
It's all about understanding those fluctuations, those deviations from the average behavior. It tells us that those fluctuations, when scaled appropriately, converge to a Gaussian process.
A Gaussian process.
Yeah, think of it like a bell curve. It gives us a way to quantify those fluctuations and understand how much the message queue might deviate from its predicted path due to the inherent randomness of the system.
So it's not just about knowing where the message queue is heading on average, but also about understanding how much it might wobble along the way.
Precisely. And that's crucial for designing robust systems that can handle the inherent uncertainties of the quantum world.
Okay, I'm starting to see the bigger picture here. We have these two powerful theorems, the functional law of large numbers and the functional central limit theorem, that give us a way to analyze both the average behavior and the fluctuations of the message queue in this entanglement-assisted communication system.
Right.
And all of this is based on this clever queuing model that incorporates those 5 propensity functions, which control the various rates of arrival, departure, generation, and decay of messages, and those precious bell pairs.
You've got it.
It's pretty amazing to see how these mathematical tools can be used to analyze such complex quantum systems.
It is. And the best part is, this is just the beginning.
There's more.
Oh, yeah. In the next part, we're going to dive deeper into the practical implications of this research. We'll explore how these mathematical insights are being used to make real-world design choices for quantum networks. It's going to get really interesting.
Well, I can't wait.
Yeah. Welcome back. You know, in the last part, we really set the stage talking about the 2Q model and those propensity functions.
The R1, R2, all that stuff.
Exactly, and how we can use stochastic averaging to make sense of those different speeds.
Yeah, that high-speed train versus the local bus analogy really helped me visualize it.
Perfect. So now I think we're ready to dive into the heavy-duty math that this paper uses to really analyze the system.
Okay, bring on the theorems. I see they talk about the functional law of large numbers and the functional central limit theorem, even martingales. It's pretty intense, but I'm trusting you to guide us through it.
I'll do my best. So let's start with the first big result, that functional law of large numbers.
Okay.
Sometimes called the FLLN for short. What it does is it tells us what happens to the message queue as the system scales up. Imagine we increase the number of messages and those bell pairs proportionally. The FLLN basically says that in the long run, the behavior of that message queue settles down and becomes more predictable.
Wait, so even though we have all these random events happening, messages arriving, bell pairs decaying the overall behavior becomes more deterministic as the system gets larger.
Exactly. And the cool thing is that predictable behavior, it's described by a specific ordinary differential equation, an ODE.
So the FLLN gives us this ODE that governs the long-term behavior of the message queue. Can you tell us a bit more about what that ODE looks like, what factors it incorporates?
Absolutely. So This ODE, it takes into account those propensity functions we talked about earlier.
The corors.
Exactly. It includes the arrival rate of messages, the classical departure rate, and even the entanglement-assisted departure rate, all averaged over the behavior of that fast-fluctuating bell pair queue. It's like, despite all the randomness at the micro level, there's this underlying order emerging at the macro level.
I see. So the FLLN gives us a way to analyze the long-term trends, to see the forest for the trees.
Precisely. Now, did they actually prove this FLLN rigorously in the paper? Because, sometimes these theoretical papers, they just kind of throw out these big results without really showing the math.
Right, right. I mean, I trust them, but I'm always curious to see how the sausage is made, so to speak.
Oh, they definitely show their work. The proof is actually quite elegant. It uses some powerful tools from stochastic analysis, like martingales and these things called occupation measures.
Oh, okay. Now, martingales, I've heard that term thrown around in finance and probability theory, but how are they used here to prove the FLLN?
So, a martingale, in simple terms, it's a stochastic process where the expected value of the process at a future time, given all the information we have now, is just its current value. In other words, it's like a fair game where, on average, you don't expect to win or lose. And in the context of this paper, they construct a martingale related to the scaled message queue length and use the properties of martingales to prove that it converges to that deterministic function described by the ODE. It's a bit technical, but the key takeaway is they really do a thorough job of proving this result mathematically.
Okay, I appreciate you breaking it down. So the FLLN gives us the average behavior, the long-term trend. But you also mentioned the Functional Central Limit Theorem, the FCLT, which deals with the fluctuations around that average, right?
Yes. Remember how we said real-world systems are never perfectly predictable? There's always some randomness, some variability.
Like those soap bubbles, popping unpredictably.
Exactly. And the FCLT, it gives us a way to quantify those fluctuations to understand how much the message queue might deviate from that nice, smooth path predicted by the FLLN.
Okay, I'm listening. How does the FCLT do that?
Well, what it tells us is that those fluctuations, when scaled in a particular way, they converge to something called a Gaussian process.
A Gaussian process? Remind me again what that is.
Basically, think of it as a continuous version of a normal distribution, that bell curve you might be familiar with. So instead of having a single random variable, we now have a whole family of random variables, each associated with a different point in time, and they're all kind of correlated with each other according to this bell curve pattern. And the FCLT tells us that the fluctuations in the message queue length, they follow this kind of pattern.
So we can use the FCLT to not only predict the average behavior of the message queue, but also to quantify the range of possible deviations from that average. It's like saying, okay, we expect the queue to be around this length on average, but it could fluctuate by this much due to the inherent randomness in the system.
Precisely. And that kind of information is crucial for designing robust systems.
Right, because if you only design for the average case, and then you get hit with a big fluctuation, things could go haywire. It's like building a bridge that can only handle the average weight of cars, but then a really heavy truck comes along, and boom, disaster.
Exactly. That's why understanding those fluctuations is so important. And this is where the FCLT really shines. It gives us a mathematical way to quantify those fluctuations so that we can design systems that can gracefully handle them.
Yeah, they actually provide a proof for the FCLT in the paper, right? What kind of mathematical machinery do they use for that?
Oh, yeah, they're not messing around. The proof is pretty involved, but again, they lay it all out very clearly. They use a combination of tools from stochastic analysis and functional analysis. Things like tightness of probability measures and weak convergence of stochastic processes. It gets quite technical, but essentially they show that the scaled and centered version of the message queue length process converges to a Gaussian process with a specific covariance structure.
Okay, well, I'll take your word for it. It sounds like they're really being rigorous in their analysis.
Absolutely. Now, remember those propensity functions we talked about earlier? The R1, R2, all of that.
Yeah, the ones that control all the rates in the system.
Right. Well, in addition to proving those big theorems, they also explore how those propensity functions, specifically those related to entanglement, affect the performance of the system. It's where the rubber really meets the road, They delve into what they call performance-based design aspects, offering engineers a sort of toolkit for optimizing these networks.
So it's not just about analyzing the system in the abstract. It's about figuring out how to actually control and optimize it for real-world applications.
Exactly. And they do a great job of showing how those mathematical results can be translated into practical design choices.
Okay, I'm really curious about that. What specific parameters do they focus on when they're talking about performance-based design?
The key ones are those related to entanglement, of course. They focus on the entanglement generation rate, which they denote as LB, and the entanglement-assisted departure rate, which is captured by R4. Remember how R4 incorporates that speed-up factor, M?
Right, M, that tells us how much faster we can send messages thanks to entanglement. It's like the turbo boost for our quantum data.
Exactly. And the higher LB is, the faster we're generating those bell pairs. And R4, well, that's influenced by both the number of available bell pairs and that speed-up factor, M. So these two parameters, OMI and R4, they really control the flow of entanglement through the system.
Okay, so by tuning those parameters, we can essentially control how much entanglement we're injecting into the network and how effectively we're using it to speed up communication.
Exactly. But here's the interesting part.
What's that?
They don't just analyze these parameters in isolation. They actually keep the classical aspects of the system fixed. So the message arrival rate, R1, and the classical departure rate, R3, those are treated as constants.
I see. So it's like they're doing a controlled experiment where they're specifically looking at how changes in those entanglement-related parameters affect the system while keeping everything else constant.
Exactly. It's a really clean way to isolate the effects of entanglement on the overall performance.
So what kind of performance metrics are they looking at? How do they measure whether a particular setting for R4 is good or bad?
Well, they introduced this concept called the effective service rate.
Okay.
It's denoted by F, and it essentially measures how quickly the system processes messages in the long run, taking into account both classical and entanglement-assisted communication. It's like the overall throughput of our quantum data highway, considering all lanes.
So a higher F means we're processing messages faster and our network is more efficient.
Exactly. And this effective service rate, F, it's directly influenced by those entanglement-related parameters, we and R4. Remember, R4 is itself influenced by the speed-up factor, M.
Right, and that speed-up factor depends on how intense our purification protocols are. So it's like we have these levers we can pull to try and optimize the system.
Precisely. But there's a trade-off here, as you might expect.
Of course, there's always a trade-off.
The more intense our purification protocols are, the higher the speed-up factor M we can achieve. But more intense purification also means we're consuming more bell pairs.
It's that delicate balance again. We want to squeeze as much juice as we can out of those bell pairs, but we also need them to last long enough to actually boost communication.
Absolutely. It's a classic resource allocation problem. And they actually provide a concrete example in the paper to illustrate this trade-off.
Oh, tell me more about this example.
Okay, so in this example, they set the classical departure rate, R3, to be AA1, or Y1 represents the size of the message queue. So the more messages we have waiting, the faster they're processed classically. That's pretty intuitive, right?
Right. It's like the more cars you have lined up at a toll booth, the faster they try to get you through.
Exactly. Now, for the entanglement-assisted departure rate, R4, they set it to be MAA1, which is similar to R3, but now amplified by that speed-up factor, M.
Ah, I see. So the entanglement-assisted rate is like a turbocharged version of the classical rate, with the speed-up factor controlling how much boost we get.
Precisely. And remember how the functional law of large numbers gave us the average or steady-state size of the message queue?
Right. We denoted that as AS, if I remember correctly.
Exactly. Well, by setting the equation that governs the evolution of the message queue to 0, we can solve for Hayes, and in this case, it depends on both A, B, and M.
So by tuning the entanglement generation rate and the speed-up factor, which we can control through those purification protocols, we can actually influence the steady-state performance of the system. That's really cool.
It is, isn't it? It's like we have this mathematical model that allows us to see how those different knobs and dials affect the overall operation of the network.
So we can set a performance target. Like, we want the average message queue length to be this, and then use the model to figure out what values of A, B, and M will get us there. It's like reverse engineering the quantum internet.
Exactly. That's the beauty of this theoretical framework. It's not just some abstract mathematical exercise. It's a tool that can be used to guide the design and optimization of real-world quantum networks.
This is really fascinating stuff. But this model, it was initially designed for analyzing entanglement-assisted communication, right? Point-to-point communication between two parties.
Right.
But you mentioned that they also adapt the model to analyze more complex scenarios like quantum switches and graph state distribution.
Yes. What's really impressive about this paper is that they don't just stop there. They show how their model can be extended to these other situations that are even more complicated, even more entangled.
Okay, I'm really intrigued now. How do they even begin to adapt the model to those more complex scenarios?
Well, the key is that the fundamental concepts of queues, arrival rates, and service rates, they still apply even in those more complicated settings. It's just a matter of understanding the specific dynamics of those scenarios and adjusting the model accordingly.
Okay, so let's start with quantum switches.
Yeah.
What exactly is a quantum switch in this context, and how do they adapt the model to analyze it?
So a quantum switch, think of it as a central hub in a network for routing quantum information.
Like a train station where entangled qubits can be directed to different destinations.
Exactly. And the challenge is to manage the flow of those qubits efficiently so that they reach their destination without getting lost or degraded along the way.
Right, it's like an air traffic control system for quantum information.
Yeah.
So how does the queuing model handle this?
Well, instead of having fixed arrival and departure rates, like in the simpler point-to-point case, now the rates at the switch depend on the network topology.
Meaning the structure of the network, how the different nodes are connected.
Right. And they also depend on the specific routing protocols that are being used. So the model has to be adjusted to capture those dependencies.
So it sounds like analyzing a quantum switch is much more complex than just looking at a simple link between two parties.
It is, but the core structure of the queuing model is still there. It's all about adapting those propensity functions to reflect the more intricate dynamics of the switch.
Okay, I'm starting to get the picture. Now, what about graph state distribution? That sounds even more complicated than a quantum switch. What exactly is that, and how do they adapt the model to analyze it?
So graph state distribution, it's all about creating these complex multi-qubit entangled states.
Oh, right, those entangled states where multiple qubits are all linked together.
Exactly. And these states, they're incredibly powerful resources for various quantum communication and computation tasks, but creating them is a very delicate process.
Right, I imagine it's not easy to get all those qubits to cooperate and form those intricate entangled structures.
It's not. And the key difference here is that the service, meaning the successful creation of the desired entangled state, it's conditional. You can only proceed if you have enough entangled qubits available and if those qubits meet certain quality criteria.
So it's like baking a cake where you need all the ingredients before you can start. You can't just substitute something else if you're missing an ingredient.
Precisely. And in the context of the queuing model, they capture this conditional service by setting the classical departure rate R3 to 0.
Oh, I see. So there's no fallback option like there was in the entanglement-assisted communication case. It's all or nothing.
Exactly. You either have enough entangled qubits to create the desired state or you don't. And the entanglement-assisted departure rate, R4, now represents the rate at which we can successfully form those multi-qubit entangled states.
Okay, so R4 is now a measure of how good we are at building those complex entangled structures. And I imagine that depends not just on the entanglement generation rate, but also on the efficiency of our state preparation protocols.
You got it. Those protocols, they involve specific quantum operations and measurements that are needed to create the desired entangled states. The better our protocols, the higher R4 will be, and the faster we can create those states.
This is all really amazing stuff. It's incredible to see how this queuing model, which started out as a way to analyze point-to-point communication, can be adapted to handle these much more complex scenarios.
It really speaks to the power of this framework, doesn't it?
It does. But we've been focusing a lot on the theoretical aspects. In the next part, I'd love to explore the practical implications of this research in more detail. How are these insights actually being used to guide the design of real-world quantum networks? All right, welcome back to the deep dive. We've been on quite a journey exploring this queuing model for entanglement-assisted communication. You know, we've talked about those two queues, all those propensity functions, those fascinating theorems. It's a lot to take in.
It is, but it's such an elegant way to analyze these systems.
Right. But, you know, at the end of the day, I'm always curious about the practical side of things. I mean, how are these theoretical insights actually being used by the engineers who are building these quantum networks?
That's the million-dollar question, isn't it? In this paper, it doesn't just stop at the theory. They actually bridge that gap between the abstract math and the real-world design choices.
Okay, I'm all ears. How do they do that?
Well, remember those key parameters we discussed? The entanglement generation rate, LIBI, and the entanglement-assisted departure rate, R4.
Yeah, those are the ones that really controlled the flow of entanglement through this system.
Exactly. And the authors, they show how you can actually tune those parameters to achieve specific performance goals.
So it's like, we're not just analyzing the system anymore, we're actually controlling it, optimizing it.
Precisely. And the functional law of large numbers, that FLLN we talked about, That gives us a powerful tool for this optimization process. Remember how it tells us the steady state behavior of the message queue?
Yeah, that average queue length in the long run, we denoted that as NS, I think.
Right. Well, by analyzing how ACE depends on AB and R4, we can see how tweaking those parameters affects the system's performance over time. It's like we have a set of knobs and dials, and we can adjust them to get the performance we want.
So it's like saying, okay, we want the average queue length to be this. What settings for leaving in R4 will get us there?
Exactly. It's like a recipe for optimizing the network. And remember how R4 is influenced by the speed-up factor, M. That adds another layer of control because we can adjust M by changing the intensity of our purification protocols.
Right, those protocols that help us combat the decoherence of those fragile bell pairs.
Exactly. It's all about finding the sweet spot, balancing the speed up we get from entanglement with the resources we need to keep those bell pairs alive.
A delicate dance indeed. But, what's really impressive is that the paper goes beyond just providing general guidelines. It delves into specific scenarios, those more complex cases like quantum switches and graph state distribution. Can you walk us through how they apply the model to those situations?
Absolutely. Let's start with quantum switches. Imagine a network with multiple nodes, and you want to route entangled qubits between them. Well, a quantum switch acts as a central hub, directing those qubits to their destinations.
This is like an air traffic control tower for entangled qubits.
Yeah, that's a great analogy, and the challenge is to manage that traffic efficiently, making sure those qubits get where they need to go without getting lost or degraded along the way.
Sounds complicated. How does the queuing model handle that?
Well, instead of having fixed arrival and departure rates like in the simpler point-to-point case, now those rates at the switch depend on the network topology and the routing protocols being used.
Meaning the structure of the network and how those qubits are being directed.
Precisely. So the model needs to be adapted to reflect those dependencies.
So it's like now the propensity functions aren't just fixed numbers, they're dynamic and depend on all these other factors.
Right. For example, the arrival rate at the switch might depend on how many incoming links there are and how fast entangled qubits are being generated at the source nodes.
Okay, and the departure rate would depend on the number of outgoing links and how quickly the switch can process those qubits.
Exactly. It's all about understanding those interdependencies and adjusting the model accordingly.
Now, what about graph state distribution? You mentioned earlier that this involves creating those complex multi-qubit entangled states.
Yes, those states are incredibly valuable for a variety of quantum tasks. They're like the building blocks for more sophisticated quantum communication and computation protocols.
Okay, but creating them sounds like a delicate process.
It is. And the key difference here is that the service, the successful creation of that entangled state, is conditional. It only happens if you have enough entangled qubits available and if those qubits meet certain quality standards.
So it's like you need all the ingredients to be present and in good condition before you can bake that cake.
Exactly. And in the model, they capture this by setting the classical departure rate, R3, to 0.
Oh, I see. So there's no fallback option like we had in the entanglement-assisted communication case. If you don't have the necessary entangled qubits, you're stuck.
Precisely. And the entanglement-assisted departure rate, R4, now takes on a new meaning. It represents the rate at which you can successfully create those multi-qubit entangled states.
So R4 is now a measure of how efficiently we can build those complex entangled structures. And I imagine that rate depends not just on how fast we're generating entanglement, but also on the efficiency of those state preparation protocols you mentioned earlier.
You got it. The better those protocols are, the faster we can create those states, and the higher R4 will be.
This is really mind-blowing stuff. We've gone from analyzing simple point-to-point communication to these incredibly complex scenarios involving quantum switches and multi-qubit entangled states.
It's amazing how far this queuing model can be pushed, isn't it?
It is. And what I find so fascinating is that even though we're dealing with these cutting-edge quantum technologies, the underlying mathematical framework is rooted in this relatively old concept of queuing theory.
It's a beautiful example of how these seemingly disparate fields can come together to solve some of the most challenging problems in science and engineering.
Absolutely. Well, I think we've covered a lot of ground today. We've explored the intricacies of this queuing model, those fascinating limit theorems, the interplay of those key parameters, and even how the model can be adapted to analyze those more complex scenarios like quantum switches and graph state distribution.
Yeah.
It's been quite a deep dive.
It has. And I hope our listeners have enjoyed the journey as much as we have.
I hope so too. You know, it's amazing to see how much progress is being made in the field of quantum communication. And what's even more exciting is that we're just scratching the surface. Who knows what incredible applications we'll discover in the years to come?
I can't wait to find out.
Me neither. Well, on that note, we'll wrap up this deep dive into entanglement-assisted quantum communication. As always, keep those minds curious, and we'll catch you next time for another deep dive into the fascinating world of science and technology. Welcome back for another deep dive. This time, we're looking at this model for entanglement-assisted quantum communication channels. And we've got some excerpts here from a paper, Stochastic Analysis of Entanglement-Assisted Quantum Communication Channels, and some figures.
Sounds fun.
Yeah. So it's kind of like faster than light messaging,
Yeah.
but with a Q,
Right.
ready to untangle this.
Absolutely, yeah. Always fascinating to see how people are using these tools to study these problems.
So just to set the stage right, we're talking about these quantum communication networks.
Yeah,
And instead of bits, we're using qubits, these quantum particles that can do things like superposition.
exactly. And that really opens up a lot of possibilities when it comes to communication, because now you're no longer restricted to just 0 or 1. You can have a combination of the two.
And then that's where entanglement comes in.
Yeah.
The spooky action at a distance, where two qubits are linked.
Yeah.
You move one, and then you instantly know something about the other.
It's like magic. It's really a key resource in quantum communication. And this paper is all about leveraging it effectively.
So they've got this 2Q system.
Yeah.
One for messages waiting to be sent, and then one for these entangled pairs, the bell pairs.
Right. So if you have a message that's waiting to be sent and you have a bell pair available, then you can use that bell pair to send the message much faster using this thing called dense coding.
Okay, so let's break down figure 1 here,
Yeah.
which is kind of depicting this 2Q system. So we've got QA, which is holding the messages. And that's the primary queue using a classical channel
Right.
by default.
Right.
And then there's QB, which is the service queue, where these bell pairs are just waiting to provide that entanglement boost.
Exactly.
So then how does that dense coding work? So one qubit can carry 2 bits of information because of entanglement.
Exactly. That's one of the remarkable consequences of entanglement. You can actually pack more information into a single qubit than you could if you were just using it classically.
So the paper dives into the math of how these queues behave using something called stochastic analysis. And there are these things called propensity functions,
Right.
R1, R2, all the way to R5,
Yeah.
which are defined in equations 1 and 2.
Yeah.
And they govern how things move in and out of the queues.
Yeah, they're all about the rates, like how fast things are arriving and leaving.
Right. So like R1 and R2,
Yeah.
those are the arrival and classical departure rates from QA.
Yeah, so like how many messages are coming in and how many are leaving through the normal classical channel.
And then R3 and R4 govern the arrival and entanglement-assisted departure rates.
Right, so R3 is how quickly those bell pairs are becoming available, and R4 is how fast we can actually use them to send messages through that entanglement-assisted channel.
And then R5 is the rate at which entanglement is lost.
Yeah.
Or unusable.
Right, because those entanglements, they're fragile things. They can decay over time.
And then R4 is like the star of the show here.
Yeah, definitely.
It's representing that accelerated service that you get when you have the entanglement.
Exactly. The bigger R4 is, the faster messages can get sent when there's an entangled pair waiting.
So then the paper gets into this heavy traffic regime
Yeah.
and uses some pretty heavy-duty mathematical tools like the functional law of large numbers, the FLLN,
Right.
and the Functional Central Limit Theorem, the FCLT.
Yeah, those are some big hammers.
So can you just kind of give an overview of what those are and why they're useful for analyzing this system?
Sure. So in this heavy traffic regime, we're looking at what happens when the queues are really loaded down. And to really understand that, we scale the system up to see these patterns emerge. And FLLN, it basically tells us what happens to the average queue lengths over a long time.
Right.
And then the FCLT kind of zooms in and looks at how much those queue lengths fluctuate around those averages.
So it's like we're zooming out to get the big picture with the FLLN.
Exactly.
And then we're zooming back in to see the details with the FCLT.
Yeah, exactly.
Now there's this equation 11 in the paper. That describes the evolution of the scaled queue length at QA. And it looks pretty intimidating with all these terms.
Yeah, there's a lot going on there.
So what are the key takeaways from that equation?
So that equation is really about how the queue length is changing over time, taking into account all these different rates we talked about, including the entanglement-assisted departures, and that G of YA term, that's capturing the overall dynamics of the queue length. And the other terms are accounting for things like the arrivals, departures, and the entanglement stuff.
So this equation gives us a way to predict how the queue length will change over time, taking into account the speed up from entanglement.
Exactly.
So how do they actually use the FLLN and FCLT to analyze this equation and prove things about the system? Because there's a lot of math involved.
So with the FLLN, they're basically showing that as you make the system bigger and bigger, the random fluctuations become less and less important compared to this deterministic trend, like that G of YA term we were talking about.
Right.
And to prove that they do a lot of careful analysis with the propensity functions and look at the stochastic dynamics of the queues.
Okay.
And then with the FCLT, they're showing that the fluctuations around that deterministic limit, they can actually be described as this Gaussian process.
So they're essentially showing that the statistical properties of those fluctuations become closer and closer to a normal distribution as the system grows.
Exactly. And that's really helpful because we have a lot of tools for working with Gaussian processes. So that lets us make some pretty strong statements about how those queue lengths are going to behave, even though there's all this randomness going on.
So even with the speed boost from entanglement, things can still get a bit unpredictable, but we have tools to analyze how wild those swings might get.
Exactly. And that's crucial when you're designing real quantum communication systems. You want to know that those fluctuations aren't going to cause any problems.
Now let's dig into figure 2.
Okay, good.
Okay, so figure 2, what is it showing us?
So figure 2 is all about how the arrival rate of those bell pairs affects the queue length. Okay.
So like how often you have entanglements available,
Gotcha.
and then how long the messages have to wait.
So in 2A, we've got this scaled queue length over time.
Yeah.
And there's the solid line, which is the deterministic limit from that FLLN.
Right.
And then all these squiggly lines around it.
Yep.
What are those?
So those squiggly lines, those are like individual simulations of the system.
Okay.
And they're showing you how much the queue length can fluctuate around that average. It's like the FCLT in action.
So they're trying to follow that straight line, but they just can't help but wander off a little bit?
Yeah, exactly. It's like they're getting pulled in different directions because of all the randomness in the system, like when messages arrive or depart.
Okay, so even with the speed boost from entanglement, things aren't completely predictable,
Right.
but at least the queue length stays within some bounds around that average.
Exactly. And that's where the FCLT really helps because it tells you how wide those bounds are.
Now, 2B is focusing on the steady state queue length.
So how does that long-term average change when we mess with the arrival rate of those bell pairs?
So this graph is really useful for figuring out how to optimize the system because it shows that the more bell pairs you have, the shorter the queue length is on average.
Okay.
So if you want those messages to get through quickly, you need a lot of entanglements available.
It's like having that dial to control the speed of the quantum express lane.
Exactly. But there's a trade-off there because things like purification, which give you higher fidelity entanglements, they can actually reduce the number of entanglements you have.
So it's about finding that sweet spot, right?
Yeah.
You want quality entanglement for the speed boost,
Yeah.
but you also need enough of them to keep things moving.
Yeah, exactly. And this paper gives you the tools to analyze that trade-off and make those decisions.
So now there's equation 19, which is described as a stochastic differential equation, or an SDE.
Yeah.
And it governs the evolution of those fluctuations that we see in 2A.
Right.
So what's the essence of that equation?
So that equation is a bit complicated. But the main thing to remember is that those fluctuations, those can be modeled as a Gaussian process. And that means we have a whole bunch of tools for understanding and predicting them.
So even though the equation itself might be a bit scary,
Yeah,
the takeaway is that we can still get a handle on those fluctuations.
exactly.
We're not just flying blind.
Right. We can actually quantify them and make sure they stay under control.
So we've talked about the math, but what about the real-world implications of all this?
Yeah, that's the exciting part.
Where could entanglement-assisted communication make a difference?
So this could be huge for things like secure communication
Okay.
and distributed quantum computing.
So starting with secure communication, how does entanglement make things more secure?
So imagine you're sending a message
Yeah.
and it's encoded in qubits.
Okay.
And those qubits are entangled with qubits that the receiver has.
Right.
If someone tries to eavesdrop and listen in on that message, they have to measure those qubits. and the act of measuring them disturbs the entanglement. And so both the sender and receiver would know that someone was trying to listen in.
It's like this built-in alarm system.
Yeah, exactly. It's like tamper-proof.
That's awesome.
Okay.
Okay, and then what about distributed quantum computing?
So with distributed quantum computing, you're basically connecting multiple quantum computers together
Okay.
to solve really hard problems.
Right.
Problems that are too big for just one computer to handle. And entanglement is what lets those computers talk to each other.
So entanglement is like the glue that holds everything together.
Exactly.
That's really cool. But there must be challenges to actually making this stuff work in practice.
Oh, yeah, definitely. Like, how do you maintain entanglement over long distances?
Right.
And what are the limits of how much information you can send?
Yeah, good questions. So maybe we can dive into those challenges next.
Sounds good.
Okay, so we've seen the potential, but let's talk about the challenges. What are the biggest roadblocks to actually making this entanglement-assisted communication work in the real world?
Well, one of the main challenges is how to maintain entanglement over long distances. It's pretty fragile. It's prone to this thing called decoherence, where the quantum state gets messed up by noise from the environment or imperfections in the channels.
So it's kind of like trying to keep a soap bubble from popping when you're carrying it across a bumpy road.
Yeah, that's a good way to put it. And the longer the distance, the harder it gets to protect those entangled qubits from the noise.
So what are people doing to try to combat that noise?
So there's this whole field of research called quantum error correction.
Right.
That's all about developing techniques to protect those qubits from the noise and to preserve the entanglement. It's kind of like having this system that's constantly monitoring the qubits and fixing any errors that pop up.
So like a little team of quantum repair robots.
Yeah, exactly. So they encode the information in a redundant way. So even if some qubits get corrupted, they can still recover the original message.
But even with error correction, are there still limits to how far we can transmit entanglement?
Oh yeah, for sure. Right now, if you want to send entanglement over long distances, you need these things called quantum repeaters.
Okay.
And those are basically like relay stations along the communication channel.
Right.
They help to refresh and extend the entanglement. It's like having these pit stops for the entangled pairs to recharge.
Like rest stops on a highway, but for entanglement.
Exactly.
Instead of snacks, they're getting entanglement boosts.
Yeah, exactly. But actually building those quantum repeaters, that's a huge technological hurdle.
Right, because you need really precise control over those individual qubits.
Exactly. So we have the theoretical ideas, but putting them into practice is really difficult.
So we've talked about those practical challenges. What about the theoretical frontiers? Like, are there still fundamental limits to this entanglement-assisted communication that we haven't figured out yet?
Yeah, definitely. One of the big questions is, what's the role of entanglement in the capacity of these quantum channels?
Okay.
So we talked about dense coding,
Right.
how entanglement can double the capacity,
Right.
but are there limits to how much entanglement can actually help?
So it's not like an unlimited speed boost.
Yeah, exactly. We don't know for sure what the limits are. There's this whole interplay between entanglement and noise and the capacity of the channel.
Right.
And researchers are still trying to understand all of that.
So it's like we've discovered this awesome tool, but we're still learning how to use it properly. What are some of the exciting research directions in entanglement-assisted communication right now?
So one thing that people are working on is developing new communication protocols that are less sensitive to noise
Okay.
and don't need as many resources.
So they're more efficient.
Yeah, exactly. More bang for your buck. And then another area is just trying to come up with new materials and architectures for building those quantum repeaters,
Right.
which is really hard.
So it's a multidisciplinary effort then.
Yeah, absolutely. You've got people working on the theory, people working on experiments, people working on the materials. It's a really exciting field to be in right now.
Sounds like it. Well, this deep dive has convinced me that entanglement-assisted communication is more than just some theoretical idea. It could really change how we communicate and compute in the future.
Yeah, I think so too. It's a really cool example of how quantum mechanics can lead to these really powerful technologies.
So next time we think about sending a message or running a computation, we should think about all those entangled qubits working behind the scenes.
It's a good reminder that there's this whole invisible quantum world that's shaping our technology in really profound ways.
Absolutely. Well, thanks for joining us on this deep dive into the world of entanglement-assisted communication. It's been a fascinating journey.
It has.
Until next time, keep exploring, keep questioning, and keep pushing the boundaries of knowledge. Welcome back, everyone, to another deep dive. Today, we're going on a journey really into the world of quantum communication networks.
Yeah, it's a fascinating field with so much potential.
It is. And we're going to be exploring a paper that takes a really intriguing approach to understanding them.
Right.
It's called Stochastic Analysis of Entanglement-Assisted Quantum Communication Channels. And it uses queuing theory to model how these networks, how they behave, how they actually function.
Yeah, the paper focuses on the probabilistic nature of these quantum events.
Exactly. And that's really where the queuing theory comes in. But before we get into the specifics of the paper, I think it's helpful to kind of set the stage for our listeners.
Right.
So quantum communication networks, they use these entangled particles, sometimes called bell pairs, and they transmit information between nodes.
Exactly. And the paper sets up a queuing model. It's got two queues, and they analyze how these messages and bell pairs are managed.
Okay, so unpack this queuing model for us a little bit. We have QA, which handles the information messages, the data we want to transmit. It's like the main line in our quantum coffee shop.
And then we have QB. That one handles the bell pairs, the entangled qubits. They make quantum communications special. QB would be like the express lane.
Got it. I like that analogy. And the paper talks about different speeds of these queues. Why is that so important?
Well, the bell pairs, they don't last very long. They decohere over time, meaning they lose their entanglement. So QB has to be faster than QA.
So it's a race against time to use those bell pairs.
Exactly.
Now, how do messages actually get sent through this system?
There are two options, really. They can be sent through a classical channel. This one doesn't require entanglement. Or they can be sent through a quantum channel, which uses the bell pairs from QB.
Okay, so it's a dynamic system where the choice depends on the state of these two queues.
That's right.
And the paper introduces these propensity functions. What exactly are those?
Yeah. Propensity functions are mathematical expressions. They describe the rates at which events occur within the queues. Think of them as the rules that govern the flow of messages and bell pairs.
Like traffic signals, speed limits of our quantum coffee shop.
Yeah, that's a good analogy. For instance, you have R1, parenthesis dot parenthesis. This represents the arrival rate of messages into QA. We can regulate this rate to control the influx of messages. Then there's R2, parenthesis dot parenthesis. This represents the arrival rate of bell pairs into QB. This rate is assumed to be constant in the paper.
Like an endless supply of those entangled particles.
Exactly. And then we have the departure rates.
Okay.
So R3, parenthesis dot parenthesis. This represents the service rate of the classical channel. It's how quickly messages are sent without entanglement.
Makes sense.
Then there's R4, parenthesis, not parenthesis. This represents the service rate of the entanglement-assisted channel, how quickly messages are sent when using bell pairs. And lastly, there's R5, parenthesis dot parenthesis. This one represents the rate at which bell pairs decohere and are removed from QB.
So we have these 5 propensity functions, each controlling a different aspect of the queuing system.
Right.
But the paper goes beyond just describing those individual processes, right? It looks at the overall behavior.
Exactly. And it uses some really powerful mathematical tools. The functional law of large numbers, or FLLN, is one of them.
The FLLN, I remember that from statistics class. It sounds intimidating.
It's actually about understanding the average behavior of the queues over time. Imagine zooming out and observing the overall flow, even though things might be changing rapidly at the individual level.
So like watching our quantum coffee shop line over an hour instead of second by second.
Exactly. And the FLLN allows us to approximate how QA, that's the message queue, evolves on average, even with all the rapid changes in QB, the entanglement queue.
And that averaging works because QB is much faster than QA.
Right.
Okay. But in real life, things don't always stick to the average. There's got to be some variation. How does a paper address that?
That's where the Functional Central Limit Theorem, or FCLT, comes in. This one zooms in on the fluctuations around the average behavior predicted by the FLLN.
So it's like looking at those individual jitters in the line length as customers come and go.
Exactly. The FCLT tells us these fluctuations are Gaussian, and it uses a stochastic differential equation, or SDE, to model them.
So we have the FLLN for the big picture average, and the FCLT capturing those finer details, those random fluctuations.
Exactly.
I know our listeners are probably eager to explore those mathematical details, so let's start with the ODE, the one that describes the average behavior of QA.
Okay.
The paper presents it as equation 11. Can you tell us about it?
Yeah, equation 11. It tells us how the rate of change of the average queue length of QA depends on a couple of things: the arrival rate of messages and the effective departure rate. And the effective departure rate is a combination of the classical departure rate and the entanglement-assisted departure rate. Each is weighted by the probability of using that particular channel.
So the ODE captures how message arrival, bell pair availability, and the rates at which messages are sent through those different channels all kind of play together.
Exactly. And to illustrate how this works, the paper provides some specific numbers for those propensity functions in Figure 2.
Okay.
And this lets us see how the average queue length changes over time.
Simulations are always helpful, I think, for really grasping how these models work in practice.
They are.
But let's not forget about those fluctuations that the FCLT captures. The paper has an SDE in equation 19 to describe them. What can you tell us about this one?
Yeah, so equation 19, it's a little more complex, but it tells us that the fluctuations in QA are driven by two main forces. One is the influence of the average behavior. It's captured by the term the partial derivative of G with respect to Y sub A of S.
So even though we're focusing on those random deviations, the average behavior still has a subtle effect.
Exactly.
And what's the second force driving these fluctuations?
That's where the Brownian motion comes in. There's a term, it's the square root of sigma f of s times b of s.
Okay.
This introduces randomness through Brownian motion. It's those unpredictable jiggles and joggles we often see with quantum events. And the square root of sigma f of s, that acts as a scaling factor, it controls the intensity of these fluctuations.
Ah, Brownian motion, always adding that element of unpredictability to the quantum world.
Right.
But this isn't just any Brownian motion, right?
Yeah.
It's scaled by this function. What's the significance of that?
Well, that scaling factor, the square root of sigma fs, it's crucial because it tells us how big those Gaussian fluctuations are. And you can see in the paper that this function depends on all those propensity functions we talked about earlier. It also depends on the solution to a Poisson equation.
It's amazing how these mathematical pieces all fit together.
Right.
We've got those propensity functions controlling the rates of various events, the Poisson equation capturing some underlying probabilistic behavior, and then the Brownian motion adding those random fluctuations. And they all come together in this SDE to describe the dynamics of those queue lengths.
Precisely.
Now, to appreciate this model, we need to look at the math behind it. The paper uses some pretty sophisticated tools to represent the dynamics of the queues,
Yes, it does.
things like ODEs and SDEs.
Right. The discussion section of the paper actually gets into the practical considerations for building these networks. And it highlights how flexible the model really is.
Yeah, that's what I was curious about, how these mathematical insights can actually lead to designing real systems.
Well, it emphasizes that the model can represent different departure rates from QA, the message queue, in a variety of ways.
So it's not just a one-size-fits-all model.
Right, exactly. And it can even incorporate things like purification, which is essential for dealing with the decoherence of those bell pairs.
Purification. So we're like refining those quantum ingredients to make them more stable.
Exactly. Purification basically combines multiple entangled states to create a new one with higher fidelity.
Like distilling a more potent quantum essence.
Yeah, I like that. And the paper explains how we can adjust the propensity function, specifically R4Y1, to account for different purification protocols.
So we can model how the rate of messages departing per bell pair is affected by the specific purification strategy.
Precisely. And they even give a specific example of an assisted service rate. It's given by R4Y equals M times R3Y1 times Y2, where M represents a speed-up factor, reflecting the average fidelity achieved through purification.
So a higher M means we're getting more out of those purified bell pairs.
Exactly. But there's a trade-off, of course. More intense purification, meaning combining more entangled states, can increase M, but it also reduces the number of bell pairs that are available.
Right, so it's a balancing act.
It is. And the paper suggests that we can use other existing models to determine the best value for M.
Okay, so we have a way to fine-tune those purification strategies. But the discussion goes beyond just purification, right?
Yeah, it also looks at the arrival rate of messages, which is represented by R1Y1, and the classical service rate, represented by R3Y1.
So we're considering the regular messages and the classical channels as well.
Right, and we can adjust these propensity functions to model different situations, like controlling how many messages come in or simulating different types of classical service.
Got it. What about the generation of those bell pairs? How is that modeled?
The paper proposes using something called an MMUQ to model how those bell pairs are generated and how they leave the system.
M, M, U, and Q. Now, that sounds familiar from queuing theory. Can you remind us what that is?
Sure. An MMUMQ basically assumes that arrivals follow a Poisson process, service times have an exponential distribution, and there are infinitely many servers.
So it's like a coffee shop with unlimited baristas, no waiting.
Exactly. And this model works well for bell pair generation because we usually assume those pairs are generated much faster than the overall system timescale.
Okay, but entanglement is delicate. Those bell pairs decohere over time. How does the model deal with that?
It models the time until a bell pair is discarded using an exponential distribution.
So the model considers both the rapid generation and the eventual decay of entanglement.
Exactly. And that's what makes it so valuable for designing actual networks. It takes those real-world factors into account.
Right. It's not just a theoretical exercise. So how can we use this model to actually make networks perform better?
By adjusting those key propensity functions.
Okay.
For example, we can analyze how different choices for bell pair generation rate or the intensity of purification, how those choices impact the network's throughput.
So we can run simulations and find the best configurations.
Exactly. And the paper talks about this concept of effective service rate. This represents how quickly messages are sent in the steady state. And this rate is affected by the entanglement generation rate, the speed-up factor M from purification, and the queue length.
I see. So by looking at this effective service rate, we can optimize the flow of information through the network.
Precisely. The paper even provides an example where they have a specific set of propensity functions, and they show how to achieve a desired steady-state queue length.
Okay, that's a practical demonstration of how this model can be used for tuning a network.
Right. And this approach can also be applied to other quantum communication applications, not just sending messages with bell pairs.
Oh, so we're not limited to just that. What other applications are there?
Well, the paper mentions things like quantum teleportation, quantum switching, and distributing these things called graph states, which are a type of multipartite entangled state.
So this model is kind of a universal language for describing quantum information flow in different situations?
Exactly, and that's one of the key takeaways. This model gives us a framework for understanding and designing efficient networks, considering all the unique aspects of the quantum world.
It's really amazing how mathematical modeling can help us understand these complex systems.
Absolutely. But we've only talked about the high-level concepts so far. To appreciate this work fully, we should probably look at some of the proofs and lemmas in more detail.
I agree. Let's start with lemma 1. What can you tell us about its role in the analysis?
Lemma 1 is all about estimating the time it takes for QB, the entanglement queue, to reach a certain length.
Okay, so predicting how long it takes for those bell pairs to back up in our express lane, so to speak.
Exactly, and it does this by focusing on the moment generating function, or MGF, of those hitting times.
MGF. It sounds technical, but it's basically a way to encapsulate information about the probability distribution of those times, right?
Exactly. And the lemma provides a specific bound on this MGF. It's denoted as fan-off and k, where p is a positive parameter and k is the target queue length. As we increase k, meaning the target length gets longer, this bound approaches 0.
So the probability of QB getting really long becomes very small.
Right. And this bound depends on important system parameters, the scaling factor n, the arrival rate of bell pairs, and their decay rate.
So we can see how tweaking those parameters would affect those waiting times.
Exactly. And the proof of this lemma uses some elegant techniques from probability theory, particularly supermartingales.
Supermartingales, those came up before, didn't they? Can you remind us what they are?
Sure. A supermartingale is a special type of stochastic process where the expected value tends to decrease over time. In the proof, they construct a supermartingale that's related to the length of QB, and by analyzing the supermartingale, they derive that bound on the MGF.
Got it. So using supermartingales to reveal patterns in the queue dynamics. And this lemma helps to show the relative compactness of those processes, which is important for proving the FLLN.
Right. Now, moving on to theorem 1 itself, the one that establishes the FLLN result. What are the key steps in showing the relative compactness of the scaled queue length process, YNA, and the occupation measure of QB, which is denoted as AIN?
Okay.
The proof is pretty complex, but I'll try to highlight the main points. First, it establishes that the sequence, YNA, is tight.
Tight.
Tightness means that the processes won't have any sudden jumps or big oscillations.
Okay.
To prove this tightness, they use Prohorov's theorem.
Another probability theory concept?
Exactly. And basically, they show that for any small number, epsilon, there's a compact set that contains the processes with a very high probability.
So we're kind of confining those processes to a well-behaved region.
Yes, exactly. And then the proof moves on to find the limit points of this sequence.
Okay.
They show that if a subsequence converges, it has to converge to a limit, YA, that satisfies certain equations.
So we're not just saying they converge, but we're describing what they converge to.
Right. And those equations actually describe the limit. YA will satisfy the ODE we talked about earlier, the one that describes the average behavior of QA. And Aturi will satisfy an equation that describes the long-term distribution of the occupation measure for QB.
So the proof not only shows that there's a limit, but it also describes that limit very precisely.
Yes, and this eventually leads to the conclusion that the entire sequence, YNA, converges to this unique limit, YA, confirming the FLLN.
So we've essentially solved the FLN maze.
Mm-hmm.
But we still need to look at theorem 2 and FCLT, where all the randomness comes in.
Okay.
What are the key points in the proof of theorem 2?
Well, it starts by showing that the sequence of scaled fluctuation processes, denoted as deleon, is tight, just like in the previous proof.
So making sure those fluctuations are well behaved.
Exactly. To do this, the paper uses a couple of techniques, including Aldis's tightness criterion and the continuous mapping theorem.
Aldis's tightness criterion.
Right. This criterion basically checks for tightness by looking at how the processes behave over small time intervals.
So examining those fluctuations on a very fine scale.
Exactly. And once tightness is established, the proof moves on to find the limit points of W. It shows that if a subsequence converges, it has to converge to a process W that satisfies that stochastic differential equation, the SDE we talked about earlier, the one that describes the Gaussian nature of the fluctuations.
So again, not only showing convergence, but also characterizing the limit.
Right, and to finalize the proof, it's shown that this SDE has only one solution, meaning the whole sequence, WE, converges to this specific Gaussian process W.
So the FCLT proof brings in a whole bunch of mathematical tools to establish this result about those Gaussian fluctuations.
It does, and it gives us a way to model and understand those fluctuations, which is essential for designing reliable quantum communication networks.
Absolutely. But before we move on, can we take a closer look at some of the key equations used in these proofs?
Sure.
They might seem a bit complicated, but I think it's worth understanding them better.
I agree. Let's start with equation 8, which defines the stationary distribution of QB, denoted as DAD. Okay, this equation gives us a formula to calculate the probability of finding QB at a certain length over a long period of time. It's a really important result that a lot of the other analyses are based on.
So equation 8 is like a picture of the long-term behavior of QB. Can you break down the equation for us?
Yeah, it states that 2z equals a normalization constant c multiplied by two terms.
Okay.
The first term is z, where ooze is the arrival rate of bell pairs, is their decay rate, and z is the Q length. This term reflects the balance between arrivals and departures in QB.
So if the arrival rate is higher than the decay rate, we expect higher probabilities for longer Q lengths.
Right.
And what about the second term?
The second term is 1z, which is the factorial of z. This term accounts for the different ways you can arrange those z bell pairs in the Q.
So the equation combines those arrival and decay rates with a combinatorial factor.
Exactly.
Yeah.
And this stationary distribution is then used in analyzing QA, specifically in the ODE that describes its average behavior.
So the two Qs are intricately connected.
They are, and that connection is what makes the model so powerful. Now let's look at equation 11.
Cool.
This is the ODE that describes how the scaled Q-length process for QA, denoted as YA, changes over time. It's at the core of the FLLN result.
So it tells us how the average Q length evolves. Can you explain the equation?
Sure. It states that the derivative of YA with respect to time is the difference between two terms. The first term is R1YA, which represents the arrival rate of messages into QA.
So that's the incoming traffic of messages.
Exactly. And the second term is a bit more complex. It combines the classical departure rate R3YA, the entanglement-assisted departure rate R4YA, and the average number of available bell pairs MYA.
It sounds like this term captures the combined effect of both communication channels and how many bell pairs are available.
Right. It basically weights the classical departure rate by the probability of not having any entanglement available, which is represented by XPAA. So when there are few bell pairs, the classical channel dominates. But when there are a lot of bell pairs, the entanglement-assisted departure rate, R4YAMY, becomes more important.
So the system dynamically switches between the two channels depending on those bell pairs.
Exactly. And this ODE gives us a really concise way to model the average behavior of QA. Now, we need to talk about those random fluctuations.
Right, those quantum events that can't be predicted by just looking at averages.
That's where equation 19 comes in. This is the SDE that describes the Gaussian fluctuations around the average behavior of QA.
Okay, so equation 19 is our tool for understanding those random fluctuations.
Right. It says that the change in the scaled fluctuation process W is equal to the sum of two terms. The first term, GYASDW, captures how the average behavior YA influences the fluctuations.
So the average behavior still matters, even when we're looking at those random deviations.
Exactly. And the second term, NSDBS, introduces randomness using Brownian motion.
That Brownian motion again, representing the inherent unpredictability of quantum events.
Exactly. This term reminds us that we can't perfectly predict everything, even if we know the average behavior.
So equation 19 lets us model that unpredictability.
Right. It helps us understand how those fluctuations affect the performance of the network.
It's fascinating how these equations can capture the complex interplay of deterministic and random behavior in the system.
It is. And these equations, along with the others we've discussed, provide a strong foundation for analyzing and designing these quantum communication networks.
This has been a really insightful exploration of this queuing model and all the mathematical tools involved. But there are even more details in the paper, right?
There are. We could delve into some more lemmas and theorems that provide even deeper insights into the system's dynamics.
So there are even more mathematical insights to uncover.
There are. The paper goes on to explore additional lemmas and theorems that provide a deeper understanding of those system dynamics.
Okay, well, let's delve into those. I'm particularly interested in lemma 2, which seems to focus on the behavior of QA, our message queue, when QB, the entanglement queue, is empty.
Right, exactly. Lemma 2 looks at the moments when we're solely relying on that classical channel because there aren't any bell pairs available.
Okay, so analyzing how that message queue grows when it's all classical communication.
Precisely. It gives us a bound on the moment generating function, or MGF, of the time it takes for QA to hit a certain length, K, starting from an empty state.
Okay.
And this bound, which is denoted as it depends on the scaling factor n, the arrival rate of messages, R10, and the classical service rate, R30.
I'm noticing a pattern here. These moment-generating functions and their bounds, they seem to be really crucial for analyzing these queuing systems.
They are. They're a powerful tool, really, for understanding the probabilistic nature of these systems and for getting those useful estimates.
So what does this bound in lemma 2 actually tell us about QA when there's no entanglement help from QB?
It says that the probability of QA getting really long really fast, it becomes smaller and smaller as K increases.
Okay.
So basically, even when we're just using the classical channel, the message queue isn't likely to grow out of control too quickly.
That's good. It suggests there's a certain stability even without entanglement. But how do they actually prove this lemma? What's the approach?
The proof uses a super martingale.
Ah, super martingales again.
Yeah. They construct a super martingale related to the queue length process of QA, and then they analyze its properties using Doomb's martingale inequality to get that bound on the MGF.
So another clever use of super martingales to shed light on those queue dynamics.
Right.
Okay. Now what about lemma 3? What does that one focus on?
Lemma 3 looks at the behavior of QB, the entanglement queue. It tries to estimate how likely it is to deviate significantly from its average behavior.
So quantifying those potential fluctuations caused by those bell pairs.
Exactly. It gives us an upper bound on the probability that the scaled queue-length process for QB, denoted as YNB, differs from its average value, which is NNB, by more than a certain threshold.
Okay.
And this bound, it actually decays exponentially as n increases, meaning as the system gets larger, those deviations become less and less likely.
So as our quantum coffee shop gets busier, those bell pairs tend to behave more predictably.
Exactly. And to prove this, they use Bernstein's inequality and some properties of Poisson processes.
So another set of powerful tools from probability theory.
Right. These lemmas and those main theorems we talked about earlier all come together to give us this really solid mathematical framework for understanding this entanglement-assisted communication network.
It's really amazing how mathematical modeling can reveal those hidden patterns and help us understand these complex systems so much better.
It is. And I think that wraps up our deep dive into this paper.
It really has been an incredible journey exploring this model, all of its intricate details, and those powerful mathematical tools.
I agree.
I hope everyone listening has gained a better understanding of quantum communication networks and how math is helping us unlock their potential.
Yes, and as we move forward with quantum technology, these mathematical frameworks will be crucial for understanding and harnessing these phenomena for real-world applications.
Absolutely. Until next time, everyone, keep exploring, keep asking questions, and keep diving deep into those fascinating corners of the universe.